Hey, welcome back to Calculus. Today we are going to talk about logarithmic differentiation. So logarithmic differentiation is a way to use implicit differentiation and properties of logarithms to differentiate, here's the key, non-logarithmic functions. So there are certain types of functions that are kind of complicated, that benefit from being allowed to utilize the properties of logarithms to rewrite them before we take the derivative, before we differentiate the function. Here are the two basic types of functions where logarithmic differentiation is beneficial. Functions that involve multiple products, quotients, and powers. Here, I'll just show me what I mean by that. Like here's an example, like A and B here, where you have like either a quotient or a product, and there's several factors on the top, or maybe several powers and factors. The first example A here, you have x squared times x squared minus 1, the radical 1/2 power. So there we have several powers and several factors. That's what I'm talking about here. Whenever you have a function that involves multiple products, quotients, and powers, or the other example where the other situation where logarithmic differentiation is beneficial is when you have a variable base function with a variable power. For instance, like right here at the example 2.10.1, we have x raised to the 5x. So both the base and the power are variable. Okay, so that's not a power function because it has a variable base. Because it has a variable power. It's not an exponential because it has a variable base. It's like a weird combination of exponential and power function. It's not either, and so you can't use the rules, the derivative rules we have for power functions, and you can't use the derivative rules we have for exponential functions. Well, I guess you could use some properties, but we won't get to that. Well, maybe we'll see it later. But this idea of logarithmic differentiation works pretty nicely. So here's the basic guidelines for this process called logarithmic differentiation. Write the function. Like a lot of times we have f of x or g of x or h of x equals the function. If you need to, write it in y equals notation instead. So instead of f of x equals, x to the 5x, write y equals x to the 5x. That's just a very superficial step. The next step is going to be to take the logarithm of both sides, generally the natural logarithm, since that's the easiest one to work with in terms of differentiation. Then apply properties of logarithms to expand the expression, to rewrite it, then differentiate according to the guidelines of implicit differentiation, because we will have an implicit function at that point. Now, here's an example to show you what I mean. Proof of theorem 2.53. Remember when we were doing exponentials? I had a theorem way back. It was theorem 2.53, and part of theorem 2.53 said that if you want to find the derivative of b to the x, that's a non-base e exponential, well, then that was equal to b to the x times natural log of, not 3, I'm not really sure why I put a 3 there, natural log of b, the base. Okay, so it's b to the x times natural log of b. That's the derivative of b to the x. Okay, so back in section 2.5, I said here, let's save this proof for later on, and because there's a nice way to prove it. And so here we are. So if we want to differentiate y equals b to the x according to logarithmic differentiation, what we do is take the logarithm of both sides, the natural log. So we take the natural log of left-hand side, natural log of right-hand side. That's step 2 here, line 2. Okay. Now the next step, the whole point of doing this is to then apply properties of logarithms. what can we say? We can say the power property of logarithms says you can bring the exponent on your base and bring it out in front of your logarithm. That's the power rule for logarithms. Okay, so we get line 3. Okay, once we rewrite according to the properties of logarithms, then we can take the implicit derivative. So notice now at line 3, we have an implicitly defined function. That is, it's not solved for y anymore. We started with an explicit function. We started with y equals b to the x, which is an explicit function. But when we took the natural log of both sides, now all of a sudden we have an implicit function because it's not solved for y. But that's no problem, because we can now take the implicit derivative of the equation. So the derivative of both sides with respect to x, notice we can factor out here on line 1, 2, 3, 4, 5. We can apply the constant multiple rule and factor out the natural log of b from the derivative, because natural log of b is just some constant. So we can apply the constant multiple rule. And then we differentiate on the next step. Now notice the left-hand side has a variable mismatch. We're taking the derivative of y with respect to x. Oh, typo alert, typo alert. What did I lose? I lost natural log. All right, let's fix this. I'll fix it before you see it. Now you're going to see on the video, of course. It's not just a y. The left-hand side is not just a plain y. It's natural log of y. So we're taking the derivative with respect to x of natural log y. Derivative with respect to x of natural log y. Now, I fixed the derivative was correct. What is the derivative of natural log y with respect to x? Okay, remember the derivative of natural log. Okay, so let's think about this. We have an outside function, an inside function. The outside function is natural log x. The inside function is y. So that's how you get natural log y. You compose natural log of x and y to get natural log y. Okay, so you take the derivative of the outside function. That's 1 over x. You evaluate at the inside function, so you get 1 over y. Then you multiply by the derivative of the inside function, so you get 1 over y times y prime for the entire derivative of the left-hand side. Okay, what about the right-hand side? Now notice there is no variable mismatch on the right-hand side. The derivative of x with respect to x, business as usual, just a 1. So 1 times natural log b just gives you natural log b. Now, of course, we want to solve this. We're using implicit differentiation. We want to solve it for y prime. So we have to do that, we have to multiply both sides by y. And so we get y prime here on the second to last line. We get y prime equals y times natural log of b. But here's the thing. Whenever we are using this process called logarithmic differentiation, the penultimate step, the second to last step of the process will always yield a derivative that has a y in it, and maybe x's and y's, but here there's just a y. But here's the key. We know what y equals, because this is where we started. Y equals b to the x. So whenever we're doing this process called logarithmic differentiation, we always need to back substitute the known value for y. We know that y equals b to the x, so we make that substitution, and there is our derivative. So since we started with an explicit function, y equals b to the x, we always need to back substitute, and that will allow us to write our derivative in terms of x only. There's really nothing wrong in particular with saying the derivative y prime is y times natural log of b, except that makes applications with it harder. if you want to say like write the equation of a tangent line or find where there's horizontal tangent lines or something like that, you need to have the derivative in terms of x only. And so that's why we prefer derivatives to be in terms of x. Now, like in the previous videos with implicit differentiation, a lot of times that wasn't possible. But for logarithmic differentiation, that will be indeed possible. Why? Again, because we started with an explicit function. We know what y equals. Y equals b to the x. And now that kind of process will always take place. All right, let's look at an example from scratch. So that's a proof of theorem 2.53, which we already knew the result of, but now we know why it's true. Now, let's look at example 2.10.1. This is one of those examples. We have a variable base to a variable power. We want to find the derivative. Now, the first step to the logarithmic differentiation process was as a superficial step, very easy, rewrite in y equals notation instead of function notation. That's all. So instead of writing f of x equals x to the 5x, we're going to say y equals x to the 5x power. Okay. Now the next step is no calculus, just taking the natural log of both sides, which is an algebraic step. So natural log of both sides, we get natural log of y equals natural log of x to the 5x. Okay. And now we can use the properties of logarithms, just like the above example. We can use the properties of logarithms to rewrite this. And we can say, again, the left-hand side, that's done for right now. But the right-hand side can be rewritten. So natural log of y, we can apply the power rule just like we did above. We get 5x. The exponent originally can be moved out in front of the logarithm like so. Now, you might think to yourself, well, why are you doing that? Why is that so much better? Well, now we have a path forward for differentiation. Whenever we have a variable base to a variable power, we don't have a rule to handle that. There is no rule that says, here's how you take the derivative. But this process will allow us to get there. Okay, so now we need to do the calculus. Now we need to differentiate both sides with respect to x. So we're going to take the implicit derivative of both sides, the entire left-hand side and the entire right-hand side, and then we proceed just like we did in all of the examples for implicit differentiation. Okay, what's the derivative of natural log y? Well, we already did that. We did that right above. The derivative of natural log y is always going to be 1 over y times y prime equals, okay, we have a product here. Okay, a couple things going on here. First of all, here, I'll do this. We have a constant multiple of 5. We can factor out that 5 and say 5 times the derivative of x times natural log x. That's always a smart move, makes the derivative, the product rule, the subsequent derivatives go a little quicker. And then, okay, let's actually now apply, so I'm going to leave the left-hand side alone. It's done for the time being. But now I'm going to apply the the product rule. X times natural log x is a product. So we need to take the derivative of the first function times the second function plus the derivative of the second function. Come on, computer. Derivative of the second function, which is natural log x, times the first function, x. All right, again, the left-hand side, we're kind of done with that for the time being, equals the right-hand side, 5. Okay, what's the derivative of x? The derivative of x is 1, so we have 1 times natural log x, just natural log x, plus, okay, what's the derivative of natural log x? Okay, and by the way, we're taking the derivative of natural log x with respect to x. There's no variable mismatch. In fact, there's no variable mismatch at all on the right-hand side. The right-hand side only has x's on it. So the right-hand side derivatives are just business as usual because we're taking the derivative of x with respect to x. So the derivative of natural log x is just 1 over x times the existing x that was there. All right. We have, again, 1 over y times y prime on the left-hand side. On the right-hand side now we have 5 times natural log x plus, okay, what's 1 over x times x? Well, it's 1. It's x over x, 1. Okay, so now I can go to my solving for y prime business. To solve for y prime, I do what? I multiply both sides by y. And if I do that, I get y prime equals 5y times natural log x plus 1. But remember, we always need to back substitute. We know what y equals. Y equals, very first step, y equals x times 5, sorry, not times, x raised to the 5x power. So we could say by back substitution, we get y prime equals 5 times x to the 5x, because we know that's what y equals, times natural log x plus 1. There we are. There is our derivative of a variable base function with variable exponent. Okay, I suppose there is another way to do this. Let's see, where are we at? We're at 16 minutes. Okay, I'll show you real fast, and then we'll cut the video at that before we do some next examples. There is another way to do this, but I would say most people prefer not this way. The other way to do it would be, okay, again, you start with your, let's see, make sure I can see it. Start with your f of x, equals 5x to the 5x. And here is what you have to know. Now to do this, you really got to you really have to be on top of your properties of exponents, because here's what you can do. You could say that, okay, you can rewrite f of x as e to the natural log of x to the 5x. That's just using the known fact that e and natural log are inverse functions. So e to the natural log of anything is equal to that argument anything. So that's just algebra, no calculus there. But here's what we can do further. We can again use that same power property and say this is equal to e to the 5x times natural log x. So we brought the exponent out in front of the logarithm. Okay? Once we've done this, now we can find f prime by applying the chain rule. So f prime, notice this is composite. So maybe over here, let's write the inside and outside function. We have inside and outside. What's the inside function? The inside function is 5x times natural log x. The outside function is e to the x. So if you just want to apply the chain rule now, we can do that because we don't have any, the point of this is we have resolved the issue of having a variable base to a variable power. Now we have e, which is a constant base, to a variable power, and that variable power includes a product rule, which we know how to do. So we resolve the trouble by simply rewriting according to the properties of exponentials, logarithms, algebra. So f prime, okay, the chain rule says you take the derivative of the outside function, the derivative of e to the x. Well, that's easy, e to the x. That's the first step of the chain rule. Second step of the chain rule is to evaluate that at the inside function. So instead of e to the x, it's going to be e to the 5x natural log x. So I just replaced that with the inside function. Times, the third step of the chain rule is to multiply by the derivative of the inside function. Now here's the takeaway. We've already done the derivative of 5x times natural log x. Remember we did that over here when we solved it using logarithmic differentiation. Here, the entire right-hand side, this is the derivative of 5x times natural log x. Oh, sorry, that's not the simplified derivative. The simplified derivative is the next step, the next line right here. That is the derivative of the right-hand side, which was, remember, 5x natural log x. Okay, so that derivative is here boxed in green. So I know what the derivative is, no reason to redo it. So we can just copy that down. It is 5 times natural log x plus 1. Okay? Now, we're done, according to the chain rule, but it's not simplified. Now, you might say, okay, I know my answer is supposed to be this, so does my answer over my new answer, does that match? And it does completely. Why? Because remember, what does e to the 5x times natural log x equal? It equals x to the 5x. So we can basically undo the algebra that we did earlier and say this is just x to the 5x times that portion, just 5, so put a 5 out front, times natural log x plus 1. And so we get precisely the same answer. As we did earlier, is one way easier? I think logarithmic differentiation is easier, but that's just my preference. Feel free to do what you like. Of course, if this is a test question, you will be responsible for at least one logarithmic differentiation question on a test or exam. So be sure to do so. If you're if a problem says solve using logarithmic differentiation, be sure to use logarithmic differentiation. Here, there's two different ways to work this, at least two different ways. But remember, if you're requested to use a certain method, then of course be certain to use that method. Okay, so two ways to solve that, but my preferred way is the logarithmic differentiation way. So in the next video, I'll do some additional examples of logarithmic differentiations, and I'll see you then. Let me know if you have any questions.